going to go ahead and get started. I assume everybody can hear me okay? Yeah, okay. So first, I'd like to just welcome everybody here today for our summer webinar. I know a lot of folks may be on vacation, but this is a continuation of our passive acoustic series that we started the last webinar in June. But I hope everybody's enjoying their summer vacations, and those that are dealing with extreme heat, smoke, fires, etc. Just please stay safe because it's been a pretty crazy summer. Also want to just acknowledge the efforts on the folks here, Kathleen, Nick, and Cassie, for all the efforts we as a team do to kind of pull this together. And it's always teamwork that makes things like this actually come to fruition. And thank the speakers in advance for their participation as well. Next slide. So just I just put this in, as a reference for folks of our steering committee and our executive sponsors. If you ever, want to reach out to them, please do. Either at info@underwatergliders.com, or you can email me. But just a reminder that there's a lot of other folks that are working behind the scenes, and we'll talk about that a little bit more. Next slide. So just our agenda for today, as you can see, I talked about, I'll do some quick administrative updates, and then we'll get into the real meat of today, which are the technical talks. We have two great speakers. We'll introduce them when the time comes. You can see them listed here, and then we'll just do a quick wrap up. Next slide. First, before kicking off our agenda, I just want to take a minute to give our deepest sympathy to Barb Kirkpatrick. A lot of you know her. She's a UG2 steering committee member and executed the first UG2 workshop. Unfortunately, she had an early loss of her husband, Gary. Gliders were a part of their family, and as you see from this excerpt from Gary's obituary, he was instrumental in leading the way using underwater gliders to track and monitor Carina brevis, the organism that causes Florida red tide, which really helped advance the community's abilities to mitigate the effects of toxic algae. In addition, Gary's career and contributions to ocean science are numerous and leaves a great legacy behind for Barb and the ocean scientific community. So a great loss, but a great person who really contributed to ocean science. So reach out to Barb if you know her and give her great, deepest sympathy. And I just wanted to acknowledge Gary today. So just real quick, some updates. As part of the steering committee, we've met twice since kicking off the new steering committee, and we stood up some sub-focus groups. As you can see here, it's very early on. We're just starting to kick off these working groups or sub-focus groups. The one here on the upper left is the website Slack content and organization. We want to take a fresh look at the website and make sure that the content is maintainable, informative, that the website becomes a useful tool. And then how does Slack complement that? Slack has been a lot of participation on Slack. Can we better organize Slack? So Jennifer Savagian here has taken the lead. She's kicked that off. She's starting to put some stuff to some documents together to have an approach to this. And the other one, data management, Jennifer Bowers with down at NCEI with NOAA, she's taking the lead of that, and she'll be just kicking that off. So she'll be reaching out as well. And then training, Hank has done some initial work with some ideas on micro-credentials through MTS and whatnot for training, but trying to understand a little bit more where the training needs are, the gaps are, and working with folks that have training programs to actually get that out better via the website. And this idea of folks just coming into the community, early career students, getting a group together and basically helping early career students understand what jobs are out there in the glider community, what opportunities are out there, and help encourage folks to really become part of the glider community. Any questions on these? These are all in their early states, like I said. Anybody that wants to participate in any of these, please reach out to info@underwatergliders.com or to myself or Cassie, and we'll get you involved with the working groups as they become, but we also will communicate as developments happen with these sub-focus groups. I'll pause for like 5 seconds to see if anybody has a question on that. Okay. Next slide. So we are having a town hall meeting at Oceans 2023 for anybody that's attending. We don't know the exact date and the time yet. It will be 90 minutes. Where since it is a technology conference, and I give credit here to Doug Wilson, who's on today, of this concept of let's sit down as a community and have a discussion about what's the future of ocean gliders. We're 20 years into the use of gliders. They've become a very common sort of standard ocean research tool, but take a look at what research needs are the gliders meeting. Where are there gaps potential to be addressable with new technology, and have a discussion between industry and users. And we're going to try and set up lightning talks between industry and users to help facilitate that discussion. But you can see the kind of list of bullets here that we're talking about. So that is please excuse me, because this is my typo. It's actually the 25th through the 29th of September for oceans. And like I said, it will be embedded into the technical program. So that will be Tuesday, Wednesday, and Thursday. We just don't know the day and time. So please, if you're coming, participate. We look forward to having folks there. We've also submitted an abstract for a town hall meeting at the Ocean Science meeting in New Orleans, and that's been accepted. And for folks that were at the workshop last September, you talked about my position in hiring an early to mid-career person. There's been a delay in that just due to funding and whatnot, but we're finally this week finishing up our first round of interviews and hoping by the end of August, we have somebody that actually will be selected and can participate in the September Oceans Conference as an introduction. Any questions on that? Okay, next slide. All right, let's get into the fun part here. We have two great presentations to be offered today. The first being Mark Bumgardner from Woods Hole on the archival and near real-time passive acoustic monitoring from Slocum gliders using the digital acoustic monitor DMON instrument. Mark is a marine ecologist, having worked on marine mammals for about 30 years. He's been on the faculty of the Woods Hole Oceanographic Institution since the early 2000s, and much of his work focuses on the ecology and conservation of the North Atlantic right whale, using a variety of approaches, including tagging, shipboard studies, and using autonomous platforms and acoustics for remote and real-time monitoring. So with no further delay, Mark, I'll turn it over to you to give your presentation. Thank you.
Great, thanks, Bill. Let me get this started. Bill, can you see my screen? Great, thank you. So thanks, it's a real pleasure to have the opportunity to give this presentation. I'm gonna start off with a little bit about myself. I'm a marine ecologist. I have a math and computer science undergrad, a master's in marine science, and a PhD in biological oceanography and statistics. And I mostly focus on the ecology of whales, including their feeding behavior, what oceanographic processes drive their distribution habitat. And as you'll see, I got roped into doing acoustics, and over the past decade or so, real-time monitoring to improve both science and conservation for right whales. So right whales are pretty awesome. They're about the size of a tractor trailer. They feed on copepods, which are tiny. And my career's research has been to try to figure out how exactly it is that they do that. We also focus on right whales because they're critically endangered. This is a population trajectory for right whales since 1990, and today there are only 340 right whales left living. The 2000s were a pretty good decade for right whales. They increased their numbers to almost 500, but the numbers have been decreasing since and precipitously declining over the past several years. The reason for this is really boils down to two things. Right whales tend to get killed by ship strikes, as well as fishing gear entanglements. There are no right whales that die of old age. Right whales, adult right whales, die from industrial accidents almost exclusively. So this is a big problem, and it sort of has fueled a lot of the development of the work that I'm going to tell you about. So I'm going to, let's get in the Wayback Machine. I'm going to go through this sort of chronologically so you can see how it is that we got to the DMON system that we use today. After I finished my master's degree, I was a research associate in the WHOI's physical oceanography department. And I became friends with a young assistant scientist at the time, Dave Frattantoni, and we actually started a poker game at the time. And most of what you'll hear is sort of the result of that early poker game. But Dave was an early adopter of autonomous platforms, including Slocum gliders, and as you can see here, an Apex float. And he's standing with Ben Hodges, who has been a big part from the start of the program that I'm going to talk to you about. I left WHOI in 1998 to go get a PhD at Oregon State to study right whales, and then came back to WHOI as a postdoctoral scholar in the biology department. And it was at that time that Dave and I resumed our poker game. But we also started talking about how we could do ecological research on whales from Slocum gliders, similar to what I had done in my PhD work, which is to look at oceanographic conditions and processes along with the distribution of whales and try to figure out why it is that whales like to go to one place versus another, how oceanographic conditions and processes were driving their distribution. We do that with shipboard studies where we look for whales and then we put like CTD in the water, and we could certainly get all the physical and most of the biological observations from Slocum gliders, but we were stuck with how are we going to get the whale observations. So the way we did this is we turned to passive acoustics, which was my first foray into passive acoustics. So just to back up, we use passive acoustics to study marine mammals because they make sounds, and they make sounds often. I'll show you a lot of what are called spectrograms in this talk. Spectrogram is just a visual representation of sound. In this spectrogram, frequency or pitch is on the y-axis, time is on the x-axis. Just to orient you, these lines would be the frequencies of the lowest and the highest keys on a piano. And in this scene, in this spectrogram, we can see actually a lot of things going on. Marine mammals make species-specific sounds, and so in this particular scene, we can see there's a 20 hertz fin whale call, there's a sei whale downsweep, there's a right whale up call, there's a humpback calling as well, and then there's dolphins squeaking up around 10 kilohertz. So we can use sound to say something about the presence of animals. And if we couple that with the kinds of physical and biological oceanographic properties that gliders can observe, we can actually start to do these sort of ecological studies. So Dave and I are really fortunate to work at Woods Hole, where we have really gifted engineers and technicians. So over the course of the year, after sort of hatching this idea, we were able to build a custom acoustic recorder and a hydrophone, integrate it with the Slocum glider, and we initiated a demonstration project. On the left, you see the Slocum glider science bay with a faired hydrophone that we developed. And then on the right, you can see Dave actually doing time syncing with the recorders. If you've ever met Dave, he doesn't do anything small. Instead of doing just one glider, he decided to throw 4 gliders at this problem. So we had 4 gliders go out on this study. So it was just for a couple of days in May of 2005. We worked in an area called the Great South Channel, just east of Cape Cod, Massachusetts, where it's an area where you can find humpback, fin, sei, and right whales pretty consistently, or at least you could back in the 2000s. So we deployed these gliders, and they did what gliders do. There's actually a nasty storm that occurred during this time, and as you all know, gliders don't really care about that. We got some great audio. This is spectrograms from 3 of the 4 gliders. And in it, you can see the exact, this is just 2 minutes of spectrogram. You can see the same humpback whale calling that's being received on each one of the gliders. There's some sei whale calls in here as well. So one of the instruments we had was a acoustic Doppler current profiler attached, strapped to the front of one of the gliders. And from it, we were getting acoustic backscatter. And we wanted that because we wanted to look at this age-old hypothesis in marine mammals studies that suggests that the behavior of prey will somehow influence the behavior of the predators. And in this case, we wanted to look at the vertical migration of Calanus finmarchicus, a copepod that both right and sei whales feed on. We wanted to look at how the diel vertical migration of that copepod might influence the calling behaviors of the whales. And so I'm not sure if you can see my cursor, but up here we have, at night, we were seeing higher abundances of higher backscatter, which we attributed in a separate study to the abundance of Calanus finmarchicus. High at night at the surface, low during the day, high again at night, low during the day, high at night, low during the day. The really high stuff is bubbles up at the surface due to the storm. At the same time, if you focus on the bottom panel, the calling rates of sei whales also changed from day to night. Higher calling during the day, lower calling during the night. So it was a relatively short study, but we were able to hypothesize that the calling behavior of the sei whales was being directly influenced by the availability, i.e. the diel vertical migration of their copepod prey. And that's the paper we wrote in 2008, which was our first paper on glider work. Okay, so one last thing that we did during that study, just to demonstrate that we could, is we did localization in post-processing of these are sei whale calls heard on 3 different gliders, and using time difference of arrival methodology, you can actually localize the calls. So just for instance, call A here, here's glider 6, glider 7, and glider 8, and using these hyperbole that indicate the time difference of arrival surfaces, you can actually come up with a localization. And we actually use this information to attribute these calls to a single whale. This could be, the A and B calls could be a call and response, but time after time, we would localize the first call to be the exact same place as the second call. And that gave us the confidence to say that these calls were actually being produced by a single animal. They were making 2 calls in a row, as opposed to 2 animals calling back and forth to one another. Okay, so I was new to acoustics, and I suddenly found myself with a lot of data to deal with. And so being the sort of math programming nerd that I am, I developed a way to automatically go through the acoustic data to find calls. And this ultimately became the low frequency detection and classification system that's documented in the paper that you see below. And it's really simple in concept, so I'll just describe it really quickly. Here's a spectrogram that has a couple of 20 hertz fin whale pulses. Those are those sort of dashes on the bottom of the spectrogram, as well as 2 sei whale downsweeps. So all the LFDCS does is it creates this spectrogram, conditions it for noise, and then draws a line through each one of the calls. We call those lines pitch tracks, and they're exactly analogous to notes on a page of sheet music. If you play music, you know what those look like. And those notes, just like the pitch tracks, describe the frequency and amplitude modulation of discrete sounds. We can take those pitch tracks and put them through a classification process using discriminant function analysis to take a guess at what is producing those calls. I also want you to notice that the pitch tracks faithfully represent what's in the spectrogram, but they do so with a lot less data. And so in practice, what we do with the gliders is the DMON generates these pitch tracks. We pass them off to the glider sends them home, and we have an analyst go through them and actually determine what species are present. But I'm getting ahead of myself. We haven't even gotten the LFDCS on the DMON yet. So we did our demonstration project. It worked out really well. And at the same time, or just a little while later, Mark Johnson, who's a really gifted HUI engineer, begins to develop the digital acoustic monitoring instrument. And Dave and I quickly realized that we're going to do a lot better with this if we partner with Mark, because Mark was and is really gifted at doing low power electronics and acoustics. And the acoustic recorder that we had built was not going to be nearly as good as what Mark was developing. So we decided to collaborate with Mark, and he was gracious and generous to collaborate with us. So we started integrating a DMON with a slocum glider in 2008. By 2009, the basic functionality of the DMON was completed, and we started porting the LFDCS, the algorithm that I just talked to you about, over to the DMON. Mark and I did that together. And then we started the first missions with DMON sort of in recording mode. So here's what the DMON 1 looks like. It's very simply a low power digital signal processor, has flash memory for recording audio, and it has serial lines that you can pass detection information from the instrument to whatever you attach it to. And in this case, it'll be a slocum glider. So we can pass detection information, status information from the DMON to the glider. So by 2012, the port of the LFDCS was complete, and we did our first deployment of this whole system, the DMON LFDCS, on a slocum glider. We did that in a habitat that's kind of nasty to visit. It's fairways offshore, and it is frequented by right whales in the late fall and early winter. And so for this study, it was only a couple of weeks at sea. We were using the same fair design that we used for our original acoustic recorder. We eventually abandoned that design because that stem was pretty fragile. It was pretty easily damaged. And we documented this study in that 2013 paper. But this was the first time we got pitch track data in near real time, and we're putting it up on a publicly accessible website. And these are actually the first right whale upcalls that we ever transmitted in near real time back on November 17th, 2012, so over a decade ago now. So this was working great, and all of a sudden I had collaborators that were like, that looks awesome, Mark, can we do that? And so I started working with folks at the Ocean Tracking Network at Dalhousie, and with Hank, who I know is on the call, and Peter Windsor at University of Alaska Fairbanks, to start doing sort of proliferating the technology and working with others to get this system out as much as possible. So in the next couple of years, we did 14 glider deployments. At the same time, we realized we're probably going to need to make more of these. And the DMON 1 was really kind of a bear to manufacture. And so we went through a redesign process of the DMON to make it easier to manufacture with a couple other minor upgrades. And this new design was dubbed the DMON 2. And then we started doing our first deployments with the DMON 2 hydrophone head, and then shortly thereafter the DMON 2 on my own gliders, on HUI gliders. So here's what we were working with at that time. So around 2015, 2016, this is the new DMON 2 hydrophone head. That's the one that's used today. There's actually a DMON 1 inside attached to this. What we were giving to collaborators, and in some cases using ourselves, was this DMON 1 in a oil-filled pressure vessel that we just hung out over the nose of the glider. And that was not an ideal thing to do, but it got the job done. So this DMON is attached by a cable to this bulkhead connector, so it's getting power and comms back and forth with the glider to the nose. No one's using this anymore, although I think Dalhousie might have one glider that still operates this way, but that's not ideal. and we've gone to this Science Bay hydrophone head and DMON2 inside since. So by 2020, I had used the DMON2 enough to be confident to give it to collaborators and make sure that, to ensure that it worked for them. And in 2020, we also started allowing Teledyne Web to sell DMON2s as an integrated sensor on Slocum gliders. So we would provide them the DMON2 hydrophone head and boards, and they would integrate them into customers' gliders and Science Bays. This is what the DMON2 looks like today. It's the same features as the DMON, but it's much more easily manufactured, and it's easier to expand its capabilities and integrate it into different platforms, which we've done, but I won't talk about today. In total, we've done, since 2012, we've done 124 missions with the DMON LFDCS system, and certainly not just at Hui, but with a lot of collaborators over the years. And this number of collaborators is increasing, as you can see in recent years, which is really great to see. So how does the system work today? It's much like what I just described. We've also integrated the system into moored buoys. Hui operates 8 moored buoys on the East Coast and 2 on the West Coast. They work very much like the gliders. Every 2 hours, they send pitch track and classification information home via the Iridium satellite to a shoreside server in my lab. The data is processed and immediately put onto the robotsforwhales.hui.edu website. That pitch track data is analyzed by a lot of different analysts. The lead analyst is shown here, Julianne Wilder, who's also on the call. So the analyst goes in, looks at the pitch tracks, again, very much the way a musician reads sheet music, and figures out what species are present. The analyst review is then shared with the world. So we put the results back on the Robots for Whales website. We send out emails and text messages to stakeholders. And then we have an API for other applications to come in and grab the data and display it in their own application ecosystems. This data is used for right whales for right whale management purposes in the US. NOAA uses this data in a program called Slow Zones for Right Whales, which is a voluntary program where NOAA, researchers either hear or see a right whale. NOAA puts a box around those sightings, and then asks mariners to voluntarily either avoid that area or slow down to 10 knots or less in those areas. And this is just a display of those slow zones for April of last year. And the yellow boxes are the slow zones that have been triggered, many of which were triggered by right whale detections from DMON platforms. In Canada, the same system is used to trigger mandatory ship speed restrictions in the shipping lanes that are in the Laurentian Channel, and they're used to close fishing areas as well. If you're wondering how accurate this all is, we published a paper evaluating this entire system on Slocum gliders in 2020, so I encourage you to check that out. And then this is, I'm nearly done. This is just some, I apologize, this is a little wordy. I'll go through it really quickly. Some practicalities if you're interested in this. So a DMON2 can be purchased from Teledyne Web. If you want to use the LFDCS, it's done through collaboration with me, because the data that comes off the instrument is designed to flow through this Robots for Whales system. You should note that LFDCS data will definitely increase your Iridium bill, because we can generate up to 12 kilobytes of data per hour. We also have customers that do record-only applications. I'll work with you on develop recording parameters. I'll generate firmware for you, and then you're good to go. I don't need to be involved. Just note that the DMON2 only has 64 gigs of flash memory. It does have lossless compression, but you're going to have to duty cycle high frequency recordings, but it's just fine for low frequency recordings for the endurances of gliders that we have today. You need to pay attention to the sensors that you use that make noise. For instance, pump CTDs are pretty notorious for getting in the way of the recordings. You want to mount the hydrophone on the top side of the Science Bay, and you want to be careful about biofouling, particularly gooseneck barnacles that can grow big enough to actually tap on the hydrophone. And finally, I'll mention that we provide this DMON2 at cost as a service to the community. I'm basically the assembler, the quality control, and the customer service. So just keep that in mind when you're looking to get a DMON2. Finally, shameless plug, I'm looking for a technician to help me with both glider work and mooring work. So if you know of someone that's really technically competent and would love to work on an interesting program, send them my way. That's it. Thanks very much.
Thanks, Mark. That was great. Yeah, I think I gotta make sure we can advertise the job on the underwear. I think we may have done that. I'm not sure.
You did. I still haven't found someone, so I'll send it to you again.
Okay, that's good.
Appreciate that.
That was great. Let me see here. I'm just going to check the chat here. Let me see. Sarek, to everyone who can see your messages, question recording on. Sarah, if you want to expand on if you want to expand on that a little bit. Okay, sorry about that. So, Sarek, I was wondering how often the hydrophone in the science base needs to be serviced.
Never. The hydrophone's self-contained, requires no servicing. The DMON2 doesn't require servicing. You just need to be, the DMON2 comes with its own lithium battery, and you just have to be sort of conscious that you need to keep that topped up. That's not a big deal. At least I haven't found it to be a big deal. We've had some battery issues of late that are a little puzzling. So we haven't figured it out yet. But if you just literally that bulkhead connector, let me see if I can zoom in here. This bulkhead connector behind the hydrophone is how you communicate with the DMON2, and you just plug that into a computer and it'll automatically charge the lithium battery. So it's really maintenance free.
Awesome. Another question here from Laura Papu. What does the DMON cost today, and can the code be ported to run on a general purpose microcontroller?
I think Jose's on. He can help me here. I think integration, the instrument and the integration is about $25K now for web to install it into your science bay. It's about that order. Can the code be ported to run on a general purpose microcontroller? Everything that I've just told you is published, so you're more than welcome to take the papers and get the algorithm from that. I'm not going to port it to a general purpose microcontroller because we don't have a need for that. We have the DMON to do that, and we have a desktop version of it as well. But you're more than welcome to do that from the algorithms in the paper.
Thanks, Mark. And then I have another question from Jason Allers. Can the DMON classify, or can you train or classify against other sounds like ship traffic, dolphins, sea lions, etc.?
Sure. So up in the excuse me, up in the Chukchi Sea, we're monitoring for bowhead whales and bearded seals and walrus. So yes, the DMON can be trained to classify other sounds. Ship traffic is a harder one. We haven't had any cause to do that, but if you go on the Robots for Whales website, we can well, maybe I can do it now. We can certainly see ship passages. Let me try these buoys. Let me try a better buoy. So we generate long-term spectrograms. That's not a good one. That ship passages are pretty easy to pick out. We haven't worked on doing it in an automated fashion just yet. And that's not on my list of things to do. Yeah, here's a good example. Let me stop sharing that. Start sharing this. So again, the Robots for Whales website is publicly accessible. This is for a buoy that's just off the coast of Ocean City, Maryland. And what you're seeing, this plot is of long-term background spectrogram, sort of what the ambient noise is. There's a bunch of things we can see in here, but these red dots here, these red areas, discrete red areas, are ship passages of large ships. This stripy thing is probably a small vessel coming by. And then you can see at nighttime, which is, you can see day night here on the indicated on the x-axis. Nighttime, we're getting these sounds that only appear at night. Those are likely some fish or crustacean that's making sound only at nighttime. That's a pretty common occurrence with these data. So someone could make a ship detector. We haven't. So
I have a quick question, Mark, more on the non-technical side, but so it's pretty amazing. Like you said, the industrial is really the part that is eliminating the right whales. I was just curious on the sort of like the actionable sort of information that goes out to the shipping traffic. You talked about the NOAA product. Is there something, in other words, there's a lot of people, not a lot, but there are folks out there collecting these data. And I guess, how do you get it out to like an electronic navigation charts or a notice to mariners, so that, you know, you can have action taken to avoid these whales?
Yeah, there's been a lot of talk about that, trying to come up with ways to deliver the whale detection information directly to mariners. I think there's a challenge. There are technical challenges with that. So there's been a lot of talk about using AIS to do that, although that's been tried many, many times, and there are real hurdles to doing that.
Yeah.
But you have to ask yourself, what is the mariner supposed to do with that information? Okay, so a glider heard a whale maybe 6 hours ago, 30 miles away from my position. What am I supposed to do with that? So I would say it's more helpful for the government to develop guidance for mariners and to transmit that instead of the raw acoustic, like the raw detection information.
Yeah.
In other words, if you're going to erect a slow zone, send every ship out there the coordinates for the slow zone, right, and have that appear on their charts. That's something that I think we really need to work on.
Yeah, I mean, to me, that's, like you just said, I mean, that's to me the actionable information that people could respond to. You know, you have to sort of simplify it, but, you know, folks aren't going to be scientists out there trying to read this. So what's the latency? Like, you go through the analysts, what would be the latency in some of this getting out to a product like that?
So right now, we only do the analysis once or twice a day. And the reason being is that the action by NOAA is not instantaneous. It takes them a little bit of time. However, the gliders are programmed to, my gliders at least, come to the surface every 2 hours, and they send the data. So we could be monitoring that every 2 hours. In fact, we use that automated classification information to trigger, if a glider comes up, sends pitch track data, and inside that pitch track data, there are automatically classified right whale calls, a text message will be sent to the analyst to say, hey, there are right whale calls. And we can use that to have the analyst. So the analyst isn't sitting at the computer every 2 hours. They can just be triggered when they get a text message. Oh, I should go to the website and I should look to see if there are right whale calls there. So we can speed this up. We just haven't had a need to do that.
Right. It's kind of like operationalizing it, sort of thing. Yeah. Yep.
And the buoys do the same thing. The buoys are calling in every 2 hours, but we've got them programmed such that we can remotely put them into a mode where they're calling in every 10 minutes. Mm-hmm. So we can share that information a lot faster too. There's just no need for that right now, or no call for it, I should say.
Yeah, if you could get this overlaid on electronic chart and almost like as quick as possible, I mean, to me, it could avoid a lot of, you know, mishaps. So yeah.
But Bill, remember the slow zones program that I described to you is a voluntary program. There are
Right.
no penalties whatsoever for not,
Yeah.
there are no carrots for slowing down, and there are no
Right.
sticks for speeding. So
That's problematic in itself too. You're right. Yeah.
exactly.
Let me see. I think we have another question from Matt Grossi. Any estimate of what percentage of mariners voluntarily slow down in the slow zones? So it kind of goes along what we were just saying. Yep.
Yeah, so NOAA just did a report, I think it came out last year, to suggest that cooperation rates are not great in the slow zones. They're less than 50%. So you can absolutely legitimately question the efficacy of this entire program. However, I will say that having platforms out there that are constantly reminding people that right whales are out there is actually helping things. So, for instance, this area, I hope you can still see my map here. The Mid-Atlantic area, from sort of Rhode Island all the way down to Cape Hatteras, is an area that has not been traditionally surveyed very much for right whales. We had very little data there. We started putting buoys there. I thought, well, maybe we'll get a couple of right whale calls. Our two most active buoys, and they're really active in the Mid-Atlantic, are off of Atlantic City and Ocean City, and those are not two areas I would have predicted would have been big areas for right whales. And we, over the course of not last year, but the year before, the winter before, we triggered 46 slow zones in this area. And what that suggests is that the existing protections for right whales just aren't sufficient. And NOAA has gone ahead and are trying to get a rule in to slow down all ships on a mandatory basis, not a voluntary basis during the winter. So this idea that you're constantly telling people there are right whales out there, is really helpful, because right whales unfortunately suffer from this out of sight, out of mind kind of thing that happens in the ocean. So yes, the existing system isn't as effective as we want, but we feel like it's at least it's providing a big finger to point at where the problem is and what the problem is constantly.
Excellent. Thank you. I don't see, just real quick, if we have any quick questions. If not, just wait a couple seconds here. If anybody wants to unmute or type something, give it about 5 seconds. And up front, I'll say, Mark, thank you very, very much. Oh, wait, I think we just got another quick question. Mark, you mentioned that you are trying to correlate ocean characteristics with presence of right whales. Is it possible they are actually avoiding the ocean elsewhere?
Avoiding the ocean in that, are there areas that are less habitable for them than others? That's certainly true. This Mid-Atlantic region, for instance.
So, but maybe it's not correlation with what's in the ocean where they are, but anti-correlation with something else where they're not. So they're trying to get away from high temperatures or things like that.
Yeah, sure. So, for instance, right whales visit the southeast U.S. in the winter because females go there to have their calves because it's relatively warm, relatively calm waters. But during the summertime, most of the right whales are concentrated in the Gulf of Maine and up into the Gulf of St. Lawrence. So yes, it's hot, and there's no food along most of the East Coast during the winter time, and there's food available to them up to the north. So yes, that's certainly the case.
All right, thanks everybody for your questions and your petition. Mark, thanks again. That was super. Thank you very much. And we'll move on to our next speaker. And as that's being pulled up, I'll introduce Lauren Biggery. Lauren is currently the offshore service manager for Alcimar in the Sea Explorer glider. Lauren worked for 15 years for the French public organization, the National Center for Science Research, CNRS, and then 10 years for the private company Alcimar. In 2008, he started the French glider team CNSRS INSU, managing up to 14 gliders for the benefit of the French scientific community. In 2014, he joined Alcimar and led the development of the product for 3 years, then started the Sea Explorer as a service team to further expand the glider usage to new players in the after-sales services team to support the community of Sea Explorer users. So Laurent, I turn it over to you and thank you.
Thank you very much. And thank you, Mark, for all your presentation, because I've always followed your work and I have always been very impressed by it. Today, I will present a project called PIACO. And this project is about detecting and doing localization of marine mammals in real time in a protected area in France called the Pelagos Sanctuary. To do that, we are using 4 Sea Explorer gliders. If we can go to the next slide, please. So I have 5 points I will address. First, why do we do that? I mean, we are a company manufacturing gliders. They usually don't do that. Secondly, I will present the project PIACO a little bit more, and I will go into hardware and software about our acoustic recording systems. We will talk about the results of the project and what to do with data quality. And then I will give you a glimpse of what the next step will be for Alcimar regarding acoustic recorders. So first, our motivation. You have to know that Alcimar is not only a company that sells glider, we are as well a service provider. And this changed completely our storyline using gliders. We work for research, defense, and marine energy. And in fact, if you only sell a product, I mean, you're mainly interested about vehicle and sensor. And when you do services, you are mainly interested about your measurement and about the science you can do with it, because you have to answer scientific questions, even when it's ExxonMobil that asks questions. In fact, those questions are highly scientific. So we have to go through all these loops. And the good thing about that is that we can go back to the vehicle and make sure all important information are transmitted to shore. And for example, the noise of the vehicle is removed from the measurement, the acoustic measurement. So it's a very close loop at Alcimar between product line and service. So next slide, our motivation to do research, in fact, comes from our participation in scientific project. To give you an idea, for example, that is 2 years now, we are monitoring the Mayotte underwater volcano for the French government. We are participating at the European projects. Some of them, Odysseus, are observatories. Some are looking more to digital twins and how the data can be aggregated with other kind of data and what kind of answer we can get from that. And we're working a lot about sensing. For example, we have installed an ADCP on the glider, and we went up to sending current profile. So we do all the calculation, and our customers, they can have direct current profiles from the surface to 1,000 meters. And same thing with acoustic. We are doing acoustics since years. So we can calculate background noise measurement, which is of interest of navies usually. And in PIACO, we will address marine mammal detection and localization. So this program is a huge program in France, because there is a region called the Pelagos Sanctuary, which is an habitat for whales. And in this program, we want to reduce the radiated noise of the ships. So to do that, there is a propeller change. There is tools for the captain to have information of his self-estimated ship radiated noise. There is as well a buoy that is installed in order to compare all ships and to give good points and bad points to the one that making more noises. And I am working mainly in the goal 4, which is about the impact of the underwater noise to marine fauna and the risk of collision with cetacean. So in the Pelagos sanctuary, we have two kind of whales. We have sperm whales, which is toothed whales, where we will study mainly the clicks, and those clicks are centered at 8 kilohertz. It's a wideband click. It's very easy to recognize, but it can be as well mistaken with other noise in the water. Some coming from propeller cavitation or ship instruments, and other animals as well. So you have to be careful in order to make sure those clicks comes from sperm whales. The second marine mammal we have in the Pelagos, if we can go to the next slide, is the fin whale. Well, the fin whale is a baleen, in fact, and then it has a complete different noise. The calls are at 20 hertz. We mainly target those ones in order to recognize the fin whales. It's a very special noise, but you have this noise travels so much in the ocean. In fact, you have a background noise, in fact, of 20 hertz pulses all the time, and it can be as well mistaken with very far marine traffic on this bandwidth. So when you want to do auto detection, you have to be careful of that. So in the next slide, I will talk a little bit about the acoustic system we have put on the glider for this project, and I will ask you first to look at the top right corner, when you can see the very front of a Sea Explorer glider with 6 hydrophones that are used as an antenna in order to record all the sounds. So you have the technical specification on the left, and you can see that we can still, it's a low power recorder. We can still stay 1 month or 1.5 months in the water. And we have 2 computers inside. We have an FPGA and we have a STM32. And this allows us to do automatic classification of noise in real time. So we have 9 classifiers. Some are meant for traffic. Some are meant for the glider noise in order not to mistake the glider noise with other noise. And some are specific to dolphins, sperm whales, and fin whales. And for sperm whales, what we do is that we have a neural network in order to recognize the clicks. And because we have an antenna and we have 6 hydrophones, not only we can recognize the click, but we can give the direction from where it's coming. So we can say that the sperm whale is in a specific direction regarding to the glider. For the fin whales, at 20 hertz, the antenna is not big enough to give a direction, but we can recognize them using image processing algorithm from the FFT, the fast Fourier transform of the acoustic signal, in order to recognize this sound. And we put a time of arrival in this sound, which means that we will be able to find a position using several gliders. So if we go on the next slide is the one, I would say the more difficult. You have to start at the top left corner, where far away at sea, you have your fleet of gliders. And inside your fleet of gliders, you have the recorder, which will do 2 things. It will record all the data because we want to use it after the mission for quality control. And this is a huge data that cannot be sent by Iridium. And then you have the artificial intelligence that is in charge of doing all the mammals detection and sending all the information through satellite about the marine mammal detected, the time of the detection, and eventually, if possible, the direction of detection when it's sperm whales. And all this goes into our supervision model, which is called Glimpse. It's a piloting system, in fact, where we do the navigation and we have the near real-time localization. In the framework of this project, we send this localization to a system called RepSet, which is a ship-to-ship information about whale monitoring. And we add our glider information, so the ships and all the vessels close by to the glider are informed about whale presence. So, and you have done a complete loop where the ship is close to the glider, and the glider tells, okay, here you have a whale. Because what Mark was mentioning is true. The ships, they are not very close one to each other. Maybe you will have 2-3 ships a day, so the information gets very quickly too old to be used. But when you have gliders in ship lanes, of course, you can tell the vessel, inform them in real time if there is presence or absence of marine mammals. So how does that work? The 4 gliders will transmit information about their detection, and depending if it's a fin whale or a sperm whale, the localization would be different. For fin whales, which is the top image at the right, it's about time of arrival. It's what Mark explained just before me. So you will do your hyperboles, so the difference of time of arrival between 2 gliders, and then you will have 3 hyperboles, and wherever the hyperboles cross is where your fin whale is. For the sperm whale, which is the bottom image at the right, you have directly the direction of arrival, and then you can say that the whale is there. So if we move to the next slide, you will see how we designed the area of monitoring, because we cannot monitor the whole Mediterranean Sea, and we decided to go on the offshore and onshore, because those 2 whales, the fin whales, lives more on offshore, and the sperm whales live more close to the shore on the shelf break. And we targeted as well region where we are supposed to encounter high noise from ship lanes. And what you see in this picture, in fact, Glimpse is our piloting tool, and the background image, in fact, are the ship lanes in the area. So you can find places where you are expected to find low noise from ship traffic, and places where you are expected to find high noise from ship traffic. And we wanted to study the difference in the presence or absence of those animals in those different areas. The total distance of the trip is about 200 nautical miles, and we do that in 20 days or so. Let's jump directly into some mission results. There you can see 2 mission results, one in November 2022 and one in January 2023. You can see on the first mission that we have both detection of sperm whales and fin whales. So the pink dots are sperm whales and the green dots are fin whales, and we can find them exactly where they are supposed to be in their habitat. Sperm whales close to the shelf break and fin whales offshore. If you look at January 2023, we did not manage to locate fin whales. That doesn't mean that we did not record fin whales, but we did not achieve to have localization of fin whales. And we have sperm whales in different areas, and this is because migration starts, in fact. So I believe there are more. They can occur in the middle of the basins, and not only on the shore. So if you go to the next slide, which should animate. So this is an animation of the very start of a mission, where you can see the triangles are the 4 gliders starting to go, and there are not information yet. Usually we do some kind of square between those 4 gliders, but I picked this example because it is for me extremely important. And Cassie, if you can hit play again, please, that would be great. No, hit play on the movie. Okay. What you see at the beginning is that you can see a sperm whale that is going towards the glider. And even though the glider are not in formation, all the points are very, very logic, one which is each other. The sperm whale is doing almost a straight line. The speed of the sperm whale is coherent with the distance. And what is amazing is that once the sperm whale passed over the network of glider, we don't hear it anymore. And the reason for that is because the clicks are very directional. And if you don't look at the sperm whale in front, well, it's much harder to hear the click and therefore to get a real position after that. So if we go in the next slide, I will talk a little bit about data quality, because it's very important for us to give good information, of course. So as a reminder on the next slide, you will see the localization on sperm whales. You remember that we do hear the direction of the sperm where the sound is coming from. So we have this direction finder. And if you look at the next slide, you will have the same example with 4 different quality parameters. So the 2 main parameters, besides detecting that the sperm whale is a sperm whale, are the score of detection and the beam width. I told you earlier that the glider knows in which direction the call has been emitted. And in fact, this direction cannot be a straight line. So what you have to do is you have to create a beam starting from the glider and looking in the direction to widen a little bit what would be a straight line. And you can decide how much the width of your beam would be. And on those examples, on the left, you have a beam width of 5 degrees, and on the right, you have a beam width of 10 degrees. And moreover, you don't need 4 gliders, in fact, to do this kind of localization. You need only 3 gliders. If you can go to the previous slide, please, Cassie. You need only 3 gliders. So you can set up your score. You need only 2 gliders, actually. So you can set up your score to be minimum 3 gliders. That would be a score greater than 2.9, and that's the first line. Or you can ask only 2 gliders information to get position. And what you see in those slides are the different results that this get. All of them would give you a position or several positions, but you will have to know what value do you want to put to this information. So for real-time application on marine mammal tracking, usually we try to minimize the number of dots and to have a very good information. But you could widen up your control quality in order to have more position if you just want to know where it could be and with less certainty. So if we go in the next slide, there you can see a detection in an area where you have several sperm whales, because of course there is not only one sperm whale. The little stars that you can see in the center of the screen are the glider position. We still have 4 gliders. And the red dots you can see are the different position of sperm whale and localization. And you can see that one sperm whale is inside the network, and this one is very easily tracked, and we can have a trajectory of these sperm whales. And the other sperm whales outside of the network are much more difficult to capture. And in this example, we have only one position, which is the left one. So if we apply the same kind of rules for fin whales, and as a reminder, I told you for fin whales, this is time of arrival that counts. We have the same kind of results. So the result would be next slide. Here you can you go next slide, Cassie, please? Okay, here, thank you. Here you can see a fin whale that is inside the network, and you can see that all the hyperballs cross very nicely, and we have a very good position. And on the next example, you can see a fin whale where we get a position, but it's very close to a glider. So for me, the position is good, but probably the sperm whale is somewhere there. But you can see this big yellow patch, so it can be very well somewhere along this line. And in the third example, which is next slide, you can see a call of a fin whale that has been received on all 4 gliders, which is coherent, but the position cannot be found, either because it's not the same fin whale, either because water propagation is unfortunately not its straight line, so it does not always work to get a position. So if you go in the next slide, there you can see the full data. So all the diamonds you see are the positions that have been transmitted detected in real time and transmitted to ships. We are trying to have 1 position per hour. And there you can see the difference between the number of position, which is probably less than 100 position for sperm whale plus fin whales. And in the table on the left, I show you the number of hole detection we have on each glider. So for sperm whale, we had in a 20 days mission, we had more than 30,000 individual detection on each glider. And for fin whales, we had more than 100,000 individual detection on each glider. And the reason why all those detections are not translated into position is the control quality you will put on that. The first thing we do on control quality is to validate the raw detections. But then our software is requested to have a sequence of detection, which is specific for each species. And if we have the same sequence on all gliders, then we can try to get a position. And depending on the score, we will validate or not this position. And that's how you have tens, if not hundreds, of individual calls of whales, and you end up with only 100 position in a 20-day missions. So if you go on the next slide and you want to think about take-home message, what has been proven with this project is that we can detect and localize whales that are as different as baleen and tooth whales. The difficulty is not the same actually, but it is feasible. You have to adapt your quality control to the need of the user. I mean, do they accept false detection, or is it absolutely not possible? Do they accept false localization, or is it absolutely not possible? And then we validate our results using the post-cruise analysis, because we record all the sound underwater. And we use this analysis in order to improve our artificial intelligence and train it again in order to have a better detection. If, for example, a whale could be mistaken with a ventus noise or with a ship that could be passing by and triggered the whale detector. The main difficulty we had on this project is to work with this STM32 computer, mainly because we want to do more calculations. And this one allows you cannot have as many detectors as we would like to have. So we want to move out of that. Not everybody knows how to write code on the STM32 computer, and this code you have to you cannot once it's in the computer you cannot play with it as easily. So we could not change all the parameters we wanted to change during the mission, especially for quality control. It does not allow us to implement customer algorithm because our customers they would like to use their own algorithm. and it's harder to implement new species and to multiply the species on the same mission, the species detection on the same mission. So what we are doing on the next slide is to prepare the next generation of gliders. So we are currently moving to a new computer. On the next slide, please. It's a Jetson computer, and this is much more friendly because there is ROS embedded inside, so it's easier to program, and it's compatible with Python, which most scientists know how to write code in Python. And what we do as well, we added a capability with this computer to do backseat driver. So actually, the science is able to pilot the glider. So if you want to follow sperm whales, for example, you can write a code that will force the Sea Explorer to follow a sperm whale as they are hearing it. And of course, it's a much more powerful computer, so you can have much more species detection with it. So we have on the next slide, I show you just the two early users that will be delivered in a few months. Those two recorder. The first one is Inestec. It's a Portuguese research center, and they want to do underwater fleet algorithm. They want to the glider to stay underwater, actually, and to be controlled by a surface vehicle. So they need to have a science base that allows glider piloting. And the second one is a non-governmental organization called SETI that works in Dominics, and they want to detect whales and to understand better their sound and how they communicate. And for that, it was very important for us to send a lot of information and to implement their own programs into our glider. And this is what they will be doing, and I will be there in 2 months to train them. And that's about what I wanted to say, and I'm very happy to welcome your questions, if any.
Thank you, Laurent. Please, anybody, either unmute or drop your questions into the chat, and I'll read them. There was a comment, I guess more so, from Kaylin Burmaster saying beautiful visualizations, and yeah, I agree. Yes, very good visualizations.
Thank you, Kaylin.
So, Laurent, you talked a little bit about you showed an example, I guess, with the glider. I can't remember if it was the fin whale or the sperm whale, but the directional component, and all of a sudden you lost contact with the whale. So I was just curious, and you did talk about a little bit on the product side of the tolerance, I guess, with false positives or false negatives. What do you have any idea, like based on the glider trajectory, where you might be missing, possible detections or anything like that? I'm not sure if I'm asking it correctly, but it's the idea that you're missing opportunities because of the directional component.
Well, that's a good question. There are several things. It's not as important for me to miss a whale than to mistake a boat with a whale, for example. So that was really the first challenge when you do that with artificial intelligence, is to make sure you have enough data sets in order to make sure that when you do an automatic detection, you have it. And this, we know we have a very good result. And funny thing is that we are used to go in deep water, and we had to perform a mission with a non-governmental organization because they had a boat, and we wanted to do a on-site experiment where they could validate our positioning. And we went flying in a 300-400 meters of water, and in fact the benthic activities triggered, sometimes could trigger our sperm whale detection. So we have to add a benthic detector in order to classify benthos and not to be mistaken with benthos if we are in shallow water. The whale, the sperm whale we are missing because of directivity of the sound is nothing we can do about. And when I mean, except to have like
Lots of gliders.
work on your network. If you need an avoidance area, an area where we work in ship lanes, so we want whales that comes from the north and whales that comes from the south. We would need to work on that. But in a study like the one with Piaco, where the main objective of this study was to demonstrate we could pass along whale position to ship directly using robotic gliders. That was the most important part for us in this study. But there is a lot of work to do still.
Yeah, thank you. Mark Baumgartner has that question. He said, great presentation, Laurent. How do you synchronize the clocks among the gliders to be able to do accurate time difference of arrival localization for fin whales?
Well, we have a GPS every time we surface. So in fact, on this experiment, the gliders stay only 1 hour underwater. So if you have a 10-6 precision clock, you're good to go. So as long as you use your GPS in order to resynchronize your recorder, I mean, you should be fine. And that's the point of being a manufacturer working with data, is that this is the kind of thing we can do because the GPS is in the glider, in the vehicle, but we ask to pass it over to science for those purposes. But you're right, time is essential.
Mark, you have anything? Does that answer it, or you want to follow on question? Okay, we've got one more from Gui Castillo, and I apologize for buggering up anybody's name, but great presentation, Laurent. What is the impact of Jetson in the mission duration, i.e. relative power consumption?
Yeah, high relative power consumption, I agree. Probably more powerful than other systems. I mean, you know what? We have a different experience with glider because we have rechargeable gliders. You know, I talked to you about the mission we do on top of a volcano. To give you an example, the mission is to monitor the water depths between 900 meters and 1,000 meters. So we are doing multi-UR depths with a ADCP, CH4 sensor, CO2 sensor, oxygen sensor, and CTD full time. So the mission duration is 2 weeks, which is ridiculously short for a glider. But we've been doing that since 2 years, and it's not very difficult because you take your glider out of the water and you plug it into the wall, and next day you're back at sea. So in fact, for me and for Alcima in general, it's more important to have a glider that is easy to use rather than to have an extremely endurance glider, because if it costs you very little money to prepare your glider and to get it in the water, in fact, you don't care that much about endurance. You use more gliders, you decimate your data a little bit if you want. I mean, there are strategies you can use to do that, but surely the Jetson Nano is more than a watt. So it's a big computer, but we believe it's worth to do it if it allows scientists to put inside their own algorithm and to do your studies, without and to pilot gliders with their backseat driving. I mean, we really believe this is part of the future of glider, is to bring more autonomy to the glider, and we will not do piloting tools that can do everything that scientists can imagine. We prefer scientists to imagine what they want and to implement it. So we try to give the key.
Right. Okay, thank you. Natalia has a question. What is the bulk glider price with the PAM system?
That's a good one. I don't sell glider myself. I believe the glider naked without sensor should be somewhere close to 150,000 euros, and the passive acoustic monitoring sensor should be any number between 20 and 30 thousand euros. But please, well, you have Pablo in US if you are from US. There is Pablo, I should have mentioned his name in my presentation, but Pablo is in charge of all this and he will give you any numbers you want. Sorry.
Very good. Yeah, I think, yeah, Pablo was at the workshop back in September. Yep.
Yeah.
Yep. So we can get his contact information to Natalia. Yep. Okay, well, thank you, Ron. I think we're getting pretty near the end here. Thanks again to our speakers. Excellent talks, excellent, visuals, great questions from the audience. Really appreciate it. I know everybody's busy and having a busy summer, so thank you for those who attended as well. I think we have maybe a quick wrap-up slide. Does anybody want to unmute and ask any quick questions? Please feel free. I guess we have just a few minutes. Okay. So I think as we move on to our next series of webinars, I'd like to sort of transition into maybe more the operational side. And that can be, anywhere from best practices to even, experiences and questions, that type of thing. So setting up possibly a panel to do that. I'm just looking for any recommendations because these are about topics that you all as the community would like to hear about. So please give me feedback, either at the email here or personally to me, that's fine. bill.lynch@noaa.gov. And also Slack is the collaboration tool. Like we said, we'll be trying to clean that up. Please go out there and visit the folks that are operating gliders and see what's going on out there. One other topic that was going to come up that I didn't mention at the town hall in September at Oceans, Tony Knapp at GERG has mentioned the idea of having a conversation about a community of glider users that get together for insurance purposes and approach, insurance providers. If you basically go in bulk, can you get reduced insurance quotes, via someone like Lloyd's of London or something like that? But, is there an interest in doing that for folks that are, wanting to insure their gliders? So that was another topic we'll probably blend into the town hall as well. Besides for that, Cassie, is there anything administratively that I missed that you need to back me up on?
No, I think you covered it, Bill. Thanks.
Thanks, Cassie, for flawless operations of the webinar. Thank you very much. It's always someone in the background keeping this moving. So thank you. And thanks everybody for coming. We'll probably be somewhere, let's see, more towards the late September, early October timeframe next time.